This lesson is about limiting reactants, and it goes with a worksheet that you have called Limiting Reactant Worksheet. Limiting reactants are the things that limit us from being able to do certain things. What to do if I have more than one given in a stoichiometry problem, or how to live in an imperfect world. The limiting reactant is the thing that limits the amount of product formed, and when I work problems with you on the board, I will typically label it with an LR. The excess reactant is the one that's present in larger amounts than you need, and even though the word excess is spelled E-X-C-E-S-S, I often use excess as my abbreviation. The amount of product made is determined by the limiting reactant. This was like on the simulation you did making the sandwiches. If you ran out of cheese first, the cheese was the limiting reactant. Here's a similar problem. You have 1 case of cake mix and 2 cartons of eggs. How many cakes can you make? Here's some information to help. There are 8 cake mixes in a case, 12 eggs in a carton. 1 mix plus 2 eggs makes 1 cake. You have 24 eggs altogether. Feel free to pause and rewind while you make some notes and go back if you need to. There are 8 mixes in 1 case, so you could make 8 cakes altogether. If we go back and look, you have enough eggs to make how many cakes? If you have 24 eggs and you need 2 eggs for 1 cake, then based on the eggs alone, you should be able to make 12 cakes. But you only have 8 cake mixes, so you can only make 8 cakes instead of 12. So the mix is your limiting reactant and eggs are the excess reactant. There are 4 or 5 questions that are very typical in these problems. First, to identify the limiting reactant, to figure out what the excess reactant is, how much of each product can actually be made, and how much of the excess reactant is left over. General procedure for solving these problems, this is just one way to do it, there are others. I suggest you make a fence post from the given to a product. You can pick any product you like. Then make a second fence post from the other given to the same product. The smallest answer wins. When you calculate the 2 answers, whichever reactant gives you the smallest amount of product is the correct one, because you can only make as much as the least amount that you can make. It's kind of like that saying a chain is only as strong as its weakest link. Well, you can only make as much of a product as your least amount that you can make. Also, whichever fence post gives you the smallest result helps you to identify what the limiting reactant is and the excess reactant. That smallest answer that you find tells how much of that kind of product can be made. Now, if you're doing a synthesis reaction, you might only have 1 product. But if there are other products from like a double replacement reaction or a single replacement reaction, you might also need to make a fence post from the limiting reactant, now that you know what it is, to the other products to see how much of those can be made as well. Sometimes you might want to know how much of the excess reactant actually gets used so you can figure out how much you have left over. In that case, you make a fence post from the limiting reactant to the excess reactant, and your answer is going to be how much of the excess reactant actually got used. Then you subtract the given amount of the excess reactant, how much it gave you at the initial part of the problem, in the word problem, in the story, minus your answer for what you calculated was used, and your result is how much is left over. This probably seems a little odd at first when you're hearing all this. It's a lot to keep up with, but we'll do some practice problems and make sure you understand. The problems that we start with on the limiting reactant worksheet are all done in moles, so you don't have to worry about masses or particles or liters of gas. But ultimately, we want you to be able to go to those different quantities. Okay, your handout that we're going to work through is called limiting reagents or limiting reactants. A reagent is just another name for a reactant. On the first problem, you have aluminum hydroxide reacting with hydrochloric acid to make aluminum chloride and water. Is this a balanced equation? It is, but you should always check and make sure. In this problem, you're given 0.15 moles aluminum hydroxide and 0.41 moles of hydrochloric acid. So 2 givens. That's what makes this different from a regular stoichiometry problem. First, we need to know what is the limiting reactant. So one method of doing this is to start by writing the givens up above the given chemical and pick a product. You can pick either one you want. You'll ultimately end up with the same answers regardless of which product you pick. Let's use water for my example. So for the first fence post, I'm starting with 0.15 moles of aluminum hydroxide, and I want to know how many moles of water that will make. So I make my fence post with 0.15 moles of aluminum hydroxide over 1, and then just do the mole ratio step. The 1 on the bottom comes from the coefficient, and the 3 on the top comes from the 3 in front of the water, the 3 coefficient. 0.15 times 3 is 0.45 moles of water. So what this means is if I use only 0.15 or like 15% of a mole of aluminum hydroxide, and I have all the hydrochloric acid in the world that I want, and I'm not going to run out, I could make as much as 0.45 moles of water. Let's see how much we can make based on the hydrochloric acid. So I put the hydrochloric acid given over 1. Do the mole ratio with that one. It's a 3:3 ratio. Notice that will simplify down. And this one gives me 0.41 moles of water. So according to the hydrochloric acid, I can only make 0.41 moles of water at the most. So between the two answers, which one is smaller? Smallest one wins. So what that tells me is the hydrochloric acid is the limiting reactant. Make sure that you don't label, sometimes students will write LR right here, but the water is not the limiting reactant. The water is a product. It's the hydrochloric acid from over here that is a limiting reactant. So I suggest you label it up here at the top on your reaction. Then you can label the aluminum hydroxide as the excess reactant by default. And we've already answered several of those typical questions. We know what's limiting, we know what's excess, and we know how much water can be made. What we still don't know is how much aluminum chloride could be made or how much aluminum hydroxide is left over when our reaction stops. So let's work on how much aluminum chloride can be made. There's a few ways to go about this. Probably the easiest is just to recognize from the equation above that there's a 1:3 ratio between the aluminum chloride and the hydrochloric acid. So you put the given, the limiting reactant, over 1 times 1/3, that's your mole ratio, and you get 0.14 moles of aluminum chloride. Now, to figure out how much aluminum hydroxide was actually used up, you could do some reasoning here and say, well, if I produce 0.14 moles of AlCl3 here, then I must also have used 0.14 moles of aluminum hydroxide because they're in a 1:1 mole ratio. So however many moles of this I made is how many moles of this I used. You can also use a fence post to set it up, and your fence post looks like this. 0.41 moles HCl over 1 mole aluminum hydroxide over 3 moles of hydrochloric acid. Your answer is 0.14 moles of aluminum hydroxide. Now that's how much got used. How much did I have to start with? 0.15. So think of it in terms of money maybe. You had 15 cents worth up here at the top. That was given. I just spent 14 cents worth of aluminum hydroxide moles. How much do I have left over? A penny. Let's try number 2. On this problem, you're given iron 3 oxide and carbon monoxide to make iron and carbon dioxide. The givens are 0.25 moles of iron 3 oxide and 0.66 moles of carbon monoxide. Let's pick iron. So here's my equation with the givens up above. I'm going to start by making a fence post from each given, from the iron 3 oxide to the iron, and then I'm going to make another fence post from the carbon monoxide to the iron and compare answers and see which one gives me the smallest answer. Okay, here's the first fence post, 0.25 moles Fe2O3 over 1, and then the mole ratio from the equation, and I get 0.5 moles, half a mole of iron. So if I use a quarter of a mole of iron 3 oxide, I can make a half a mole of iron, which I should have been able to figure out because up here at the top I have a 1:2 ratio. Why don't you hit pause and set up the next fence post yourself, and then hit play again, see if you get it right. Here's the second fence post. 0.66 moles of CO over 1, 2 moles of Fe over 3 moles of CO. The moles of CO cancel out, it gives you 0.44 moles of Fe. So which one's smaller? 0.44 moles of Fe. So what's the limiting reactant? That's the carbon monoxide. What's the excess reactant? That's the iron 3 oxide. How much carbon dioxide can be produced in this equation? We'll start with your limiting reactant, 0.66 moles of CO over 1, 3:3 mole ratio of CO to CO2. Since this is 0.66 moles and it's the limiting reactant, then I should also have 0.66 moles over here because of the 3 and the 3 are the same coefficient. How much excess reactant is used? Well, from the limiting, you have to use the limiting reactant here, over 1, to the excess reactant. Okay, my fence post is going from here to here. I find out that 0.22 moles of Fe2O3 are actually used. So how much is left? Well, you see, I was given 0.25 moles. I just used 0.22 moles in that equation, so I have 0.03 moles of Fe2O3 left over at the end. And I also know that 0.66 moles of CO can be made. So I know what's limiting, what's excess, how much of each product can be made, and I know how much of the excess is left over at the end. Okay, you try the worksheet, do number 3 and 4, and then bring it to me to check.